welcome to Techie with Santhosh. I would like to thank my family, my friends, and my mentor, Professor Surendran GCT Coimbatore, and Almighty my God. Today's topic of interest is stress strain relationship, that is elastic constant and strain energy. First, we have to know what is meant by a stress. Stress is a simple thing. We can say it as an internal resistance offered by a body per unit area is called as stress. What is the difference between the stress and a strength? Strength is the material property, stress at failure. Therefore, at the failure condition, the stress produced in the material at the failure condition is a strength. And also, strength is a material property. Stress is a geometric property. Here, I would like to explain stress strain relationship, stress strain diagram for the mild steel component. So, this is the graph. This is the y-axis. We can say it in stress, and the x-axis in strain. If with the If the bar of a diameter d and having a length as per the ASTM standard is loaded in the universal testing machine, the stress strain graph will plotted like this. From 0 to A, it is called as a proportionality limit, and A to B, it is a elastic limit, and B point, after the B point, it goes to plastic limit. C is the upper yield point, D is the lower yield point, E is the ultimate point, where F is the failure point, and G, generally the G term is called as a true stress strain point. How it is coming means, in the stress strain relationship, the stress calculation, stress is equal to load by area. After the ultimate stress point, the diameter or the cross section of the bar is keep on reducing. If we take a instantaneous diameter means the graph is to be plotted at the higher position than the point E. That is why it is called as a true stress and true strain. Okay, here let me explain what is meant by true stress. The load per instantaneous area is called as true stress, and strain is the change in length along the original length at the instantaneous time. That is called as a true strain. From this point, from this graph, we have an idea about Hooke's law. Hooke's law, it is defined as with when the material is loaded within the elastic limit, the stress is directly proportional to strain. Or elastic limit, we can say it is a proportional limit. With when the material is loaded within the proportional limit, the stress is directly proportional to strain. So this definition is very appropriate. Therefore, the stress strain relationship is, from the slope we can say get it d sigma divided by dE is equal to constant. The constant is the one of the material property that is called as an Young's modulus. For the design purpose, the failure point is called upper yield point. This point you have to note it down. In the design condition, we don't go with the ultimate point or the failure point. We stop our design up to the upper yield point, that is point C. The brittle materials, we can say the brittle materials are also can elongate. The elongation is very limited to 0.002 percentage of the elongation. We can say 0.002 percentage of elongation are available in the brittle material. Next, we are going to see three types of materials. One is a isotropic material. Isotropic means the property is same in all direction, and also four elastic constants are required to relate this stress strain relationship. The four elastic constants are Young's modulus, bulk modulus, and rigidity modulus, and Poisson ratio. To define the material, two elastic constant, minimum two elastic constant is enough. Two independent elastic constant, that is the thing. Here, mostly mu Poisson ratio is equal to 0.25 if mu is equal to y3, that is, sorry, 1 by 3. If the mu is equal to 1 by 3, K Young's modulus is greater than bulk modulus. If mu is greater than 1 by 3, if mu is less than 1 by 3, E is greater than K. If mu is greater than 1 by 3, E is less than K. And 2G is less than E, and 3K is more than E. Therefore, E by G is G by E is more than 2, and K by E is more than 1 by 3. So this is the relationship for the isotrophic materials. Next, anisotrophic material. Anisotrophic material, the properties are different in all directions. Therefore, it requires 21 elastic constant to define the material and stress strain relationship. The orthotrophic material, the mutually perpendicular directions are having a same property, or that is called as orthotrophic materials. Here, the orthotrophic means 9 elastic constants are required to define the stress strain relationship. Ortho means 9 elastic constant, as well as orthogonal means 90 degree. Okay, here I would like to share the Egk relationship. E Young's modulus, G shear modulus, K bulk modulus. If E is equal to 2C into 1 plus mu, this is the relationship for E and C. We can notate the shear modulus as C, as G, as N. So for the shear modulus, there is a three notations are available. Please do know. And the relationship between E and K, that is Young's modulus and bulk modulus, is here E is equal to 3K 1 minus 2 mu. And Egk relationship, we have a two Egk relationship. One is E is equal to 9kg divided by 3k plus g, or we can say 1 by 9E is equal to 1 by k plus 1 by 3g. Here in mnemonic code, this equation we can remember like ஒரு காலி மூணு கோலி 9 பேரை எடுத்தாங்க. Like that, we can give 1k plus 1 by 3g is equal to 1 by 9e. Here, I wanted to know that, let you know that there is a common units for pressure, Young's modulus, bulk modulus, shear modulus, as well as stress. All the units are in Newton per millimeter square. Next, very important factor, Poisson ratio. Poisson ratio mu is equal to lateral strain divided by linear strain, or a longitudinal strain. We can say as a mnemonic code law Li, LA by LI, law Li. Okay, we have a very famous song, very famous humming like la li la 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 la, like that. From that humming you can get the Poisson ratio is the lolly, that is called as lateral strain divided by linear strain. The Poisson ratio is 0 to 0.5. The theoretical Poisson ratio limit for an isotrophic elastic solid, it is from -1 to 1 by 2. This you have to know. The Poisson ratio for the different materials have been specified here. Mu is the Poisson ratio for the rubber, 0.5 to 0.48. It is a perfectly plastic condition. For a cork, the Poisson ratio is 0. For the cement 0.1 to 0.2. Dilatant, there is a negative Poisson ratio. For the dilatant material, there is a negative Poisson ratio. For the mild steel, 0.25 to 0.33, and the cast iron, 0.23 to 0.27, and for the glass, 0.2 to 0.27. For the aluminium is 0.33, and for brass 0.34. For gold, it is 0.44. It is for a pure gold, it is 0.44. For the material like paraffin, rubber, clay, or uniaxial condition, the perfectly compressible linear elastic materials are having mu is 0.5. Next, axitic having -1. Next is a generalized Hooke's law. The generalized Hooke's law having a relationship between, we know that stress and strain. Here the strain E1 is equal to sigma 1 by E minus mu into sigma 2 by E minus mu into sigma 3 by E. Likewise, sigma E2 is equal to sigma 2 by E minus mu into sigma 1 by E minus mu into sigma 3 divided by E. As we say, E3 is equal to sigma 3 by E minus mu into sigma 1 by E minus mu into sigma 2 by E. Here we have a relationship sigma 2 is equal to minus mu into E1. Next, very important thing, strain energy. Strain energy is due to suddenly applied load. When the suddenly applied load to gradually applied load, we can say the strain energy becomes 4 times greater than suddenly applied load, and the elongation is 2 times greater than suddenly applied load, and the stress is 2 times more in suddenly applied load when compared to gradually applied load. Here the 5 factors are very important. One is resilience. Resilience is the energy stored in the material when it is loaded within the proportional limit. We have a formula U is equal to half into sigma into delta V, or a strain VV. From the derivation, the strain energy, the resilience, the strain energy is sigma square V divided by 2E. Proof resilience is the maximum strain energy that can be stored in the material within the proportional limit. So, here we have a story to remember the proof resilience. நம்ம ப்ரூஃப் பண்ணணும்னா மேக்ஸிமம் எஃபர்ட் எடுக்கணும். ஓகேவா? நம்ம ப்ரூஃப் பண்ணணும் அப்படின்னா we have to take the maximum effort. That is called the maximum up to proportional limit, the maximum energy stored. From this story we can remember that. Next, modulus of resilience is proof resilience per unit volume of the material up to proportional limit. Therefore it is for a unit volume, therefore the volume is 1, the strain energy U is equal to sigma square divided by 2E. Okay, next one is a toughness, ability of the material to absorb energy by virtue of plastic deformation. Therefore the toughness is the maximum strain energy that can be stored in the material up to fracture point. So for this, a famous Vadivelu dialogue is there. இவன் எவ்வளோ அடித்தாலும் தாங்குறான்டா. தட் மீன்ஸ் எவ்வளோ அடித்தாலும் ஃபெயிலியர் ஆகிற வரைக்கும் எவ்வளோ அடித்தாலும் அந்த மெட்டீரியல் இட் கேன் அப்சர்வ். தட் இஸ் கால்ட் அஸ் அ டஃப்னஸ். நெக்ஸ்ட், மாடுலஸ் ஆஃப் டஃப்னஸ். யூ கேன் சே the area under full stress strain curve is called as a modulus of toughness. That means maximum strain energy that can be stored in the material up to the fracture point per unit volume. So that is called as modulus of toughness. Similarly, the strain energy for the different conditions are here. The strain energy in terms of load and deflection, U is equal to half P into delta. And strain energy in the term of torque and angle of T into theta, strain energy stored in a body, U is equal to sigma square V divided by 2E. Therefore, the work done is W is equal to P into delta. Strain energy is half into W, that is called half into P into delta. Here, I would like to quote here the Young's modulus of the different material. For a timber section, 10 gigapascal, aluminum 60 to 80 gigapascal, brass 80 to 90 gigapascal, copper 90 to 110 gigapascal, and cast iron is 100 to 160 gigapascal, wrought iron 190 to 200 gigapascal, steel and nickel 200 to 210 gigapascal. From this, an important thing, even we have seen the Poisson ratio, even though the plastic, we naturally, the plastic rubbers are elastic in nature, whereas the material point of view, the high elastic material is a mild steel or a steel. I hope that you have all enjoyed the video. Please like, share, and comment the topic. If you have any doubt, please let me know in the comment section and let we discuss. Thank you.